In this video, I'll walk through the definitions of difference between two sets, as well as symmetric difference of two sets. And we'll take a look at example 2.30, which gives us a couple sets and asks us to compute, among other things, these operations. So first off, just definition of difference and symmetric difference. So given two sets A and B, A minus B is the set of all elements that are in A, but not in B. So in terms of Venn diagrams, that looks like, right? So I collect everything that's in A, but I exclude the elements that are in B. So that means this intersection between A and B, I don't want to include that. I don't want anything that's in B. So this is just this part. That's the Venn diagram for A minus B. Now at the same time, we could compute B minus A. So this would be the set of all elements that are in B, but not in A. So that would look like this, right? Everything that's in B, but not in A. So that's B minus A. Notice that these two things are different from each other. That is, A minus B and B minus A are not the same thing. And so what we have here is our first non-commutative operation. A minus B is not equal to B minus A. It's not necessarily equal. There's some situations where they would be equal. I'll let you think about when that would be, when these would actually be equal. So this isn't saying that they're always not the same. It's saying that they're not always the same. It's possible they're the same, but not in every situation are these two things the same. And so this is not commutative. Not a commutative operation. And I believe that's the first one that we see that's not commutative. Now the symmetric difference, similar to difference, but it's symmetric. Notice how just doing A minus B, it's kind of lopsided. B minus A is kind of lopsided. So the symmetric difference, which we take the union of A minus B with B minus A. So what that looks like is A minus B. So there's that A minus B. And I take the union with B minus A. So that's all this stuff. And this would be the symmetric difference of A and B. A symmetric difference B. Now there are some other notations that go along with symmetric difference. If you're reading other textbooks, you might see A triangle B. This is the same thing as the symmetric difference. So notice we're using this O plus notation again. Why is this? So I want you to think about it for a little bit. Why are we using the same notation? Remember what we used this for before. This was the exclusive OR operation. Remember, P exclusive OR Q, P exclusive OR Q, was true if this meant P or Q, but not both. That's the same thing that's happening here with the symmetric difference. That is, X is in a symmetric difference B if and only if, or maybe I'll say it like this. X is in symmetric difference of A and B. I don't want to use X is in. I just want to write out with set builder that this is the same thing as it's the set of all X such that X is in A exclusive or X is in B. So X is in A or X is in B, but not both. This is the same thing. Now notice how I said that. That actually suggests an identity here, that this is the same thing as X is in A or B. So X is in the union, A union B, but not both. So that is, I want to exclude the elements that are in both. So A union B minus A intersect B. These are all really the same way of expressing, or different ways of expressing the same set. So that's difference and symmetric difference. Now let's take a look at an example of this. So here I have A equal to all of the integers between 1 and 10, inclusive. And B is the set of all integers between 5 and 15. Again, inclusive. So 5 and 15 in particular are in B. 1 and 10 are in A, along with everything in between. So for A minus B, now this is a common misconception that I've seen students make before with set minus, is they take elements of A and subtract elements of B. So they would say have 1 minus 5 in here. -4, they would say, would be in the difference. That's not what's going on. The difference between sets is totally different than the difference between integers. So we're not taking the difference between any integers here. We're just taking all the elements of A and removing the ones that are also in B. So that is A minus B. So let's see, what's in A? Everything all the integers between 1 and 10, and then I want to take away all the integers between 5 and 15. So that would be 1, 2, 3, 4. 5 would not be in it, even though 5 is in A. 5 is also in B, and so I'd have to exclude that. Same with 6, 7, 8, 9, and 10. They're all in A, but they're also in B, and so those are all excluded. Now, it's okay here that B contains some elements that A doesn't have. I don't want to say write their negatives. For example, -11 isn't in here. I don't want to write those. I just want the elements that are in A, but not in B. And so that's just these 4 elements, 1, 2, 3, and 4. For B minus A, so go the other way, we'll see again that these are not commutative. All the elements of B, but not any of the elements in A. So let's see. 5 through 10 are in both B and A, right? So I don't want any of those. Again, I want to remove anything that's in both of them and just keep the elements that are exclusive to B. So that would be 11, 12, 13, 14, and 15. So 5 elements in B minus A. Now A union B, we know how to do. This would be 1, 2, it's anything that's in either of these, all the way up through 15. So I'll go 14, 15, I'll use ... here, all of those integers. The intersection would be what? 5. 5 is in both, 6 is in both, 7's in both, 8, 9, 10 are each in both of A and B. And now let's figure out the symmetric difference. So that's A minus B union B minus A is our definition of this. And so let's just take the union of A minus B and B minus A. So this is 1, 2, 3, 4, not 5, 4, along with 11, 12, 13, 14, and 15 would be symmetric difference of A and B. Now notice, as I said before, that this is the same thing as A union B minus A intersect B. And so here we can see that explicitly. I take A union B and I just remove all of the elements that are common to both A and B. And what am I left with? This set, which is the same thing as a symmetric difference, B. In the next video, we're going to prove this claim in general, that the symmetric difference, oh, actually, no, we're not going to prove that exactly. We're not going to prove this one exactly. You should think about why this is true in general. We'll prove something slightly different in the next video. All right, see you there.